All right. A path, we call that a path. A path from I to J is a sequence of transitions that begins in I and ends in J. All transition probabilities in the sequence are non-zero. If all the transitions in the probabilities, transition probabilities are non-zero. So to show some examples, let me use this transition probability matrix. Let's draw the graphical representation for that. So how many states do we have here? Two, three, 4, and 5, because we have 4 rows and 5 columns. So we draw an arrow from one state to another if the probability is not 0. So row 1. From 1, we go only to 2 and 3, because only 1, 2, and 1, 3. Sorry, we go only from 1 and 2, we go to 2. So 1 to 1, 1 to 2. From 2, we go to 1 and 2. From 3, we go to 3 and 4. 3 and 4. From 4, we go to 3, 4, and 5. 3, 4, 5. And from 5, we only go to 4 and back to 5. And we usually put the probabilities on the arrows. All right. But I don't put them here so that because we are mainly concerned with the concepts here. So a path from IJ. For example, a path from 1 to 2 is, or can be, this, a path from 1 to 2, or it can be this. That's also another path. It says a sequence of transitions that begin in I and end in J. The green one begins in 1, stays in 1 for another time period, then goes to 1. It's a sequence of transitions. So in 2 transitions, eventually went to 2. Or a path from 3 to 5. 3 goes to 4, remains in 4, remains in 4 again, then goes to 5. That's a path. Okay, next, a state J is reachable from a state I if there is a path leading from I to J. So can I say 3 is reachable from 2? Is 3 reachable from 2?
No.
No, because there is no path from 2 to 3. There is, obviously I cannot connect them. But 4 is reachable from 3 and 5 and 4 itself. I and J, we would say, communicate if J is reachable from I and I is reachable from J. So I want to add something here. For example, if I add a new, if the probability of going from 1 to 4 is not 0, do you think 1 and 4 communicate? You can put your answers in chat too. 1 and 4 do not communicate because there is not a path from 4 to 1. there is a path from 1 to 4, but not from 4 to 1. It says reachable. Both have to be reachable from one another. J is reachable from I if there is a path leading from I to J. There is no path that starts from 4 and ends in 1. 1 and 2, they do communicate because there is a path from 1 to 2, one from 2 to 1. And is there a path between 1 and 5? Or would you say no? Because yes, there is a path from 1 to 5. Because from 1 you go to 4, then from 4 you go to 5. But can I say 1 and 5 communicate? No. You can go from 1 to 5, but there is no way you can go from 5 to 1. You can go from 5 to 4, but then there is no path from 4 to 1. Okay. So far good, huh? Next, a set of S in a Markov chain is a closed set, if no state outside of S is reachable from any state in S. Oh, that's a little complicated, but it looks very easy. So let's remove that. Actually, let's keep it. It says we basically call a set of states. For example, 1 and 2, 1, 2, and 3. We call a set of states a closed set if they communicate with each other, but they do not communicate with others. For example, in a class of 20 students, there are 3 that only talk to each other. They don't talk to others, right? We would say that they are a closed set. But if one of those 3 talks to one of the other students, other 17 students, but let's say this, there's a classroom, there are 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. There are 20 students here. These 3 here, they only talk to each other. But they do not talk to anybody else. So far, I can say, yes, they are a closed set. It matches the definition. Now, let's say there is another student here that one of those students is really interested in and tries to communicate with that student. But that other student doesn't communicate back, doesn't talk back to them. Then, can I still say that those 3 are a closed set? Yes, because although this student talks to this student, but the other student doesn't talk back, so I cannot say these 2 communicate. Therefore, these 3 are still a closed set. If this other student talked back, then the definition wouldn't match these 3. We would say these 3 are not a closed set because one of them communicates with someone outside. Now, can I say 1 and 2 are a closed set? Why not? It's just
because they talk to number 3.
Because 1 talks to 4. One there is a path from 1 to 4, but 4 there is no path from 4 to 1. Therefore, I cannot say 1 and 4 communicate. So 1 and 2 are still. Oh, sorry, I shouldn't say communicate. Reachable. So let me correct the previous example first. I thought this was communicate. Let me underline that. No state outside of S is reachable. So let me go back to the previous example. So there is another group of 4 students here. So those 3 I cannot call them a closed set because one of them talks to another student in another group. And that student does not talk back. So these four are truly a closed set because none of them, no other student outside of them is reachable, or in other words, none of these talks to another student. But these three are not a closed set because one of them, because a student outside of that group is reachable. Like this student gives the information to this one student. Back to this original example that we had, 1 and 2 are not a closed set because there is a state outside of these that is reachable from 1. But 4, 3, and 5 are a closed set because they communicate with each other and there is no states outside of them that is reachable from one of these. Okay, hopefully it's clear now. All right. Now, this is the most important definition. These were all a prereq for this so that we can understand this definition. A state I is a transient state, If there exists a state J that is reachable from I, but the state I is not reachable from J. For example, look at this. A state 4 is reachable from 2, but 2 is not reachable from 4. So I can say that 2 is transient. It means you can go back and forth within these two states, but once you leave them, once you leave these two, once you're here, there is no going back for these two. Therefore, I say these are transient. Or in the example that we had in the recorded lecture, we had 2 unpainted balls, and once you painted both balls, there was no way you could go back and have an unpainted ball. So those states that had 1 or more unpainted balls are transient because eventually they will not exist anymore. You will never go back to those states anymore. How about 4, 3, and 5? Are they transient? No, because there is no way that you leave 4 and never be able to come back. If you leave 4, there is always a chance that you come back to 4. You go to 3, there is a chance that you come back to it. You go to 5, there's a chance that you come back to it. Or 3. If you leave 3, you may go to 4, stay in 4 for a while, and then go to 5 for a while. But there is still a chance that you go back to 4, and then from 4 you go back to 3. So it's not transient. But 2, there is a chance that you leave 2, go to 1, then go to 4, and once that happens, there is no coming back. So only 1 and 2 are transient. These 3 are not transient. And if a state is not transient, we call it a recurrent state. So 3, 4, 5 were recurrent, 1 and 2 were transient. Just note that assuming that this arrow exists. If it didn't exist, like this, according to this transition probability matrix, not according to this transition probability matrix, everything I said was based on this diagram with this added arrow here, with that added probability, non-zero probability. Okay. Next one. A state I is periodic with period k greater than 1, 2, 3, 4, or so forth. If k is the smallest number such that all paths leading from a state I back to a state I have a length that is a multiple of k. Okay, that's too complicated. Let's look at this example. 1, 2, 3, 4. All right. What happens? Let's find out some path that leave 1 and come back to 1. For example, this is 1. This is the path. Go here, then to 3, come back to 2, come back to 1. What is the length of that path? It's 4. I don't like that color. It's 4. What is the length of this path? You go from 1 to 2, 2 to 3, 3 to 2, 2 to 4, 4 to 2, 2 back to 1. What's the length of that path? 1, 2, 3, 4, 5, 6. Let's draw a third path. A simple path going from 1 and leaving 1 and coming back to 1 is this. I can go to 2 and come back to 1. What is the length of that? That's just 2. Here you see that they are all multiples of 2. 2 is 2 times 1. 6 is 2 times 3. 4 is 2 times 2. So this 2 is k. Now read the definition again. A state I, here a state 1, is periodic with period k, positive, if k is the smallest number such that all paths leading from a state I back to a state I have a length that is a multiple of k. The length of all these paths that leave 1 and come back to 1, they are all multiples of 2. 2 is the smallest number, smallest multiple. Then I call 1 a periodic. It has a lot of applications in electrical engineering. A lot of systems follow that, actually. Follow this pattern. 2, 3, and 4 are also periodic. Just as a tip, whenever you see that, this is just based on my experience, it may not be true, but if I add this probability, which is if one of the states can go back to itself, usually none of them will be periodic. It breaks this law, this pattern, just as a tip. Okay, and if a state is not periodic, if a recurrent state is not periodic, it's called aperiodic. All right. So now that we learn this, we get to this definition. A chain is said to be ergodic if all states in a chain are recurrent, aperiodic, and communicate with each other. So for a state to be ergodic, all of them have to be recurrent, which means they're not transient. If you leave them, there is always a way to come back. None of them is periodic. They are aperiodic, which means the length of path that comes back to itself for each state is not a multiple of 2, 3, 4, or something. And they all communicate with each other. Every pair of states that you choose, there is a path from one to another. Okay, so let's find out if these states are ergodic. P1. Let me draw it. How many states? 3. Because there are 3 rows, 3 columns. Positive numbers means arrows. 1 to 1, 1 to 2, 2 to 1, 3 to 2, 3 back to 3. So, do you think if all the states are recurrent? Oh, 2 also goes to 3. So all the states are recurrent because there is no way you can leave 1 and never be able to come back to 1. Same thing for 2 and 3. Are all the states aperiodic? Yes. For example, look at 1. This is one path. 1, 2. The length of that path was 2. This is another path. 1. This is another path. 1, 2, 3, 4. Okay. These are not 1, 2, 4. I can do another one. 1, 2, 3. These numbers are not multiples of a number. So same thing for 2 and 3. They are not aperiodic and they all communicate. There's a path from 1 to 2, 2 to 1, 1 to 3, 3 to 1, 1 to 3, 1 to 3, and then 3 to 1, and 2 to 3, 3 to 2. So I can check this as periodic. How about the next one? How many states? One, 2, 3, 4. 1 to 1, 1 to 2, 2 to 1, 2 to 2, these two. So, are all the states recurrent? Yes, all the states are recurrent because if you leave 1, there is always a way back to 1. If you leave 3, there is always a way back to 3. Are they aperiodic? Yes. For example, one path, the path that leaves 1, this is a path of length 1. And this is the path of length 1. This is 1, 2, 3, and 1, 2. So they're not recurrent. That's true for all of them. They're all the same. But do they communicate with each other? 1 and 4, they don't communicate. 2 and 3, they don't communicate. 1 and 3, they don't. So this is not ergodic because they do not communicate. How about the last one? 3 states, 1, 2, 3. 1, there's a path from 1 to all of them. 2 goes to these 2, and 3 goes back to 2 and back to itself. 2 doesn't go to 3. And yeah, this one, they are all recurrent. You can leave 3 and then always come back. They're all aperiodic. The tip that I gave you, because we have these usually, it means that they're not periodic. And they all communicate with each other. There is a path from 1 to 3 and then 3 to 1. 2 to 1, 1 to 2, and 2 to 3, 3 to 1. What is the path from 2 to 3? For example, this. You go to 1 first, then 1 to 3. And there is a direct path from 3 to 1. So this one also qualifies as ergodic.